thanks all for joining. So we have some really interesting talks today. So thank you, Russell, Rebecca and Stamatina for agreeing to give them. So I think to start with, we'll just give a very brief overview of the EBS area of the RSO discipline. So just introduce myself, I'm Matt, I'm a research manager at NWS. Majid, would you like to introduce yourself?
Hello everyone, thanks for joining. I'm Majid Sadeghi, a reader in geotechnical engineering and academic lead for the discipline.
Just before we get started, we are recording this to put on the website, so if you don't want your faces to appear or anything, please turn your cameras off. Okay, so the first thing I want to do to start with is just to give a bit of a reminder what the RSO structure is. So essentially we have the RSO core team, which really drive forward the research project. And then around that, we have a range of different disciplines that cover off all kind of topics that NWS are interested in for geological disposal. And in each discipline, we have an academic discipline lead and then one or more NWS employees. And the idea really is to kind of drive academic research in a way that's really interesting from an academic perspective, but also provides really useful outputs for NWS as well. So I have highlighted 3 different disciplines here as well. Because traditionally, engineered barrier systems incorporates all engineered barriers within geological disposal system, but in the RSO we kind of split it across a range of different disciplines. So the engineered barriers systems discipline really focuses on the backfill materials and access way seal materials. But then we also have the subsurface engineering area, which is all about the constructability of the GDF and include things like liner systems, rock bolts, that kind of thing. And then on the other side, we have material sciences, which is really focused on understanding wasteform, evolution, and containing materials. And obviously, there needs to be a good link between all 3 disciplines because of all the interfaces that can occur between each of those types of materials. So I'll just hand over to Majid now.
Thank you. So the remit of this discipline is basically to assist NWS to develop a better understanding of the performance of engineered barrier system and materials, specifically in the context of UK geological environment. Considering that there have been recent developments in site location, the importance has become more and more. So the focus is primarily on backfill materials and access way seal materials, as the processes are inherently coupled and in the form of multi-physics. We are interested in developing better understanding of coupled thermal, hydraulic, mechanical, and chemical or geochemical, geobiological processes that are occurring within the barrier system, and in particular backfill and buffer or the seal materials. We are trying to encourage developments of fundamental research from across the length scale, from molecular to field experiments, to fill the gaps between the scales and processes that are of interest. Go to the next slide, please.
Oh, yeah. Thank you.
Thank you. So as part of our developments, we are in particular interested in the coming year to develop a community of practice. And for that, we are organizing a network opportunity and a workshop that provides an opportunity for academics and industry to engage with the topic, understand the challenges from the NWS point of view, and discuss potential UKRI and other funding routes. And this is under developments, and please sign up to the RSO mailing list if you are not, and we look forward to having everyone for further discussions on this topic. Thanks. Pass on to Matt.
Cool. Thank you. So the last slide from us is really just to highlight the 2 kind of topics we're looking at today. So we've got Russell here to talk about analogues. It's a really important part of our safety case. So we can provide quantitative evidence that engineered barriers work, which can be hard to do in experimental work, so the short time frames. And then the other aspect we're looking at is performance of different backfill materials at high temperatures. So at the moment, we place thermal limits on our illustrative backfill, which is bentonite in high heat generating waste concepts of 100 to 125 degrees, depending on the concept. And that's really to prevent any kind of alteration reactions that will impact the ability of the bentonite to meet its safety functions. But now you want to see this bentonite or other materials can be used at much higher temperatures so that we can basically optimize the footprint of a GDF. So by placing the wastes close together, and that can have significant financial environmental cost savings. Or alternatively, an option is to place wastes, younger wastes within the GDF and that are hotter as well, and reduce interim storage costs. So unless there's any questions, I would suggest we pass on to Russell, because I think everyone would rather hear from him than me. So I'll shut up now. Thank you.
Good afternoon, everybody. I'm Russell Alexander from Switzerland. I'm a marine chemist by background, which explains why I live in Switzerland. I'll say no more than that. Today I've been asked to introduce analogues in general to you, and also just to give you a rather quick tour of natural and archaeological analogues of the EBS. I've deliberately put a lot of information in each slide. Don't worry, I'm not going to go through them word for word. The idea is rather later, if you are interested, you can go back through them yourself and read them in more detail. There's also a huge list of references at the end for the same reason. Unfortunately, I can't control this from here because I've got a terrible Wi-Fi system, so Sam's going to help me out. Could the next one, please, sir? So I'll just look at my one here. So, as you know, the GDF EBS is considered robust, but to justify that view, we've got to try and demonstrate that all conceivable processes have been taken into account. For engineered systems, and I'm sure most of you came across a bridge somehow or other today on the way to the meeting, we don't think about it. We know they're safe because we've got experience in building them. We've been doing it for a very long time. You can't say the same for a GDF. We've got two semi-constructed ones at the moment. There's SFR and WIP. So we don't have that background to have the confidence that, you know, we know a bridge is going to stay up because we've been building them for so long. GDFs are something different. So we need to try and build confidence by a wide range of means. And the next one, please, Sam. Why analogues? Well, it's one of the tools we use to build confidence. As we say, no examples of an aged GDF yet exist, but it is possible to identify natural systems and archaeological systems which involve processes which are similar, otherwise analogous, to those that are expected. And by that, we can then hopefully provide both, Matt said qualitative, but there are cases when actually can produce quantitative evidence which we can present to a wide range of stakeholders. Next one, please, Sam. There's various definitions for analogues. My preferred one goes back to 1986 from Bernard Combe and Neil Chapman. An occurrence of materials or processes which resemble those expected in a proposed geological radioactive waste repository. I've listed a couple others here. The one that I've scored through is just complete nonsense from the IAEA back in 1989. But believe me, there's been a lot of rubbish written about analogues, so you should be aware of that now. And don't take it all at face value. Next one, please, Sam. Technical definition, basically we can provide a method of testing understanding of long-term processes, because obviously we generally are looking at geological systems. The very minimum, we're looking at archaeological systems. The other main thing about analogues, of course, it provides a method for the extrapolation of lab and modelling results to the whole overall system. And we're extrapolating from simple and I would say highly disturbed laboratory systems to the complex geological systems. In particular, we're looking from short experimental timescales and spatial scales and going to the repository relevant scales. Next one, please, Sam. So basically, why analogues? As I said, we'll link the short-term lab studies, medium-term in situ, to the geological periods that we require for the safety case. We're also looking at realistic spatial scales, compared with lab and even URL scales. In general, we're also accessing the true complexity and heterogeneity of real systems, which we tend not to do otherwise. And a final one, it's much easier to understand analogues in general compared with safety case models. I worked for NAGRA in Switzerland, the Swiss implementer, for 10 years. And there was almost nobody in the building, apart from the safety case group, could actually understand what they were doing with the models. So even some of the engineers there, we could actually get things across them with the use of analogues. Next one, please, Sam. Now, there's various strides behind analog studies. I've called them hard and soft. They are generally nowadays considered in safety case guidelines. If you look at the NEA 2004-2014, for example, the idea is they can fill gaps in mechanistic understanding, derive additional data, additional to the laboratory, more relevant temporal and spatial scales. We can reduce conservatism in the safety case and give you many, many examples of that. It also helps us to assess the robustness of the GDF. Are we really confident that this kind of slightly strange system we're constructing will work? Next one, please, Sam. Soft ones, staff training is often used. I was at NAGRA, we involved a lot of students within our analog program to get them hands-on experience. People like Placeva and JAE have used analogues as a way of training people for site characterization methods, for example. Stakeholder confidence building, NIREX, back in the last century actually, used, for example, images of Hadrian's Wall to explain to people that concretes can last for a very long time. Safety case confidence building, Placeva's most recent safety cases, some good examples there. They call their analog evidence complementary considerations, and that's in a reference list. That's worth a look. In some countries, there's actually a legal requirement. The NRA, so the Japanese regulator, and STUC, the Finnish regulator, within their regulations, you have to include some assessment of analogues. Next one, please, Sam. One thing we should keep in mind, though, a lot of people haven't done this, you have to use your analogues within an integrated approach. So you look at the analog information, look at alongside the URL data, your field tests, your lab studies, to develop overall system understanding. You can feed it into the safety case models themselves. You can feed it into the confidence in the overall understanding in the safety case models, and it all helps develop a broader, better, or broader based, I would say, safety case. So integrated, not just something sitting on its own. Next one, please, Sam. So today I will focus very much on analogues analogues of the EBS. NWS asked me to address fuel, canisters, bentonite, also concrete. Could be concrete for actual waste encapsulation, but also, obviously, depending on the host rock, we might need quite a lot of it for construction processes. So I'll cover more or less those areas. And as I say, I'll give you examples. I won't spend too much detail on them, but hopefully there'll be enough information for you to go and have a look yourself if you're interested enough later. Next one, please, Sam. And this is definitely one I'm not going to go through in any detail. I just wanted to show that analogues have been used in the safety case for quite some time. The oldest here on this list is KBS3 from the Swedes back in 1983. I should mention this is actually an extract from Table 3.3 in the NWS Analog Strategy Report, which is just about to come out. I can't remember the actual title of it now, but that will be available shortly. So I won't go through this in detail. I just say that many safety cases over the last 40 years have already used analogues for, as it says here, conceptual model development, actual model testing, and direct data input. So it depends on what you're looking at, and there are lots of examples there. And the next one, please, Sam. There's also some here. Right at the end, I've added these in red because I'm actually in that report. I have to go run back and do it quickly. And I thought they were interesting as well because they're recent examples. The third bottom one, we actually used information from the Macron natural concretes in Jordan to significantly reduce conservatism in the assessment of concrete longevity. That was for SKB. The second last case is it's in Posiva stuff, which has just come out, it's just been published this year. And the very last one is actually, we're doing it right now with NAGRA. We're looking at all available EBS information. It's still rather open, so which is why I put question marks there. It's just to show that as far as organisations such as SKB, Posiva, and NAGRA, it's still very much an active tool, and is also clearly within NWS's plans for the future. Next one, please, Sam. So we can start with some actual waste forms, vitrified waste. Natural glasses have been studied as analogues since the early 60s. But in my humble opinion, in general, the data are of limited value, mainly because the natural gas chemistry is really quite dissimilar to vitrified waste. You can argue that, in general, the fact that we have very, very old natural glasses, I mean, that example down in the bottom left there, that sits in my office, a lump of 60 million year old obsidian from the Rossamull. You can say that the fact we have very, very old glass provides confidence, and people have argued that we have gained some information on degradation processes. And I would agree with that, but I would say the data are still of limited value because the chemistry is really significantly different. Next one, please, Sam. Magnox reactors aren't only in the UK, Italy, Japan, and believe it or not, North Korea have them, or similar ones. But basically they burn metallic uranium. Now, metallic uranium definitely does not occur in nature, and so for once there are no natural or even archaeological analogues. So we won't consider that particular waste form any further here. And the next one, please, Sam. Spent fuel longevity in general, radiolysis and fuel dissolution. Most of the work on this has been done at a particular site in Canada called Cigar Lake. It's the richest uranium ore body in the world. It sits 400 meters deep, and the ore is up to 60 weight% uranium oxide. It's a quite incredible place. And this was, next one please, Sam. This was a site of some work back in the 80s and 90s, and pushed very much by SKB and at the time AECL of Canada. They looked at radiolysis and fuel dissolution. The radiolysis studies were quite good, as it showed that the models at that time were massively overestimating potential radiolysis, and it really changed that particular angle of the Swedish safety case, led them to developing significantly better codes. The fuel dissolution was something the same, that the fact that Cigar Lake is 1.2 billion years old, and they show very, very little dissolution at all, really. And again, it showed that, in effect, the models used at the time were really way over conservative and producing way more dissolution than was quite realistic. I have added uncertainties and limitations because although there are many examples of radiolysis are known, the only GDF relevant data produced today are the Oklo natural reactor site in the Gabon and Cigar Lake, but there's been any work on spent fuel stability in this century. And it's like the improvements in analytical methods and thermodynamic database could change these 25-year-old conclusions somewhat. Sam, could you go back one, please, just for a second? The previous slide where you see Cigar Lake sitting there, it's 400 meters deep. Now, at the time, back in the 80s and 90s, the claim was you couldn't see any evidence for it on the surface. And that's true. I mean, it was found through gravitational methods, but there was at that time no sign of any uranium. But the methods are so much better now that there is actually quite a clear footprint on recent work produced by one of the Canadian universities. I think it was Waterloo, I can't remember. So when you're looking back at some of the old information old analog studies, just have to be aware that sometimes the conclusions will have changed a little bit by now. Right, thanks, Sam. If you could jump forward to 2 now, to the one with the iron and steel containers. So, iron and steel, some quick archaeological analogues. Those nails on the left, again, going back to Nirex days, they used them. I've actually held these guys in my hand. They're quite stunning. They're from the Instituto, the most northerly legionary fortress in the Roman Empire, Instituto in Persia. But if you look at the list on the right, you can see 2 things. One, we're looking at iron artifacts. There's no steel here. So while we get some nice information on corrosion rates and such information, it is iron. Some are low carbon iron, admittedly, but it is still iron. And it's relatively young because it's archaeological. You know, we're going back 2,000–3,000 years perhaps. But there is lots of information in the literature. And that's just a few examples there. Next one, please, Sam. When it comes to natural systems, there's a lot less information, mainly because native iron is pretty unstable in near-surface geological environments. And when they do occur in nature, they tend to be in rather unusual things like weathering of meteorites, weathering of native iron inclusions in a really strange basalt there from Disco Island in Greenland. So it's difficult to put that data in context of a GDF, for example. Corrosion of iron placer deposits, they're relatively easy to find, but of course we don't really know the origin of the placers, and there's also generally a lack of information of their history, you know, the time they've been in those placer deposits, for example. There are cosmic meteoric dust in abyssal oceanic plains and in Lake Baikal. And then there's serpentinized ultrabasic rocks. I've worked on a lot of them myself. There, the problem is the iron is very finely disseminated throughout the system, or it's mineral lattices. So, in general, they are useful just to say yes. It gives us a good feeling because, for example, you've got some of the stuff, say, from Lake Baikal, 160 million years old, but they're not terribly analogous. That limits their applicability to a degree. Next one, please, Sam. We do have 2 recent steel analogues. These are literally hot off the press, and they're both from Scotland, just by chance. The top one, natural system, it's a 62 million year meteorite ejecta in clay. The clay is not a bentonite, but it does actually have quite a bit of montmorillonite. And the steel is actually quite similar to carbon steel. This picture's from the author of the overview paper on it, Tony Maladowski. And if you really sit and look at that picture quite hard, I'm sure you can start to hear the midges buzzing as it was being eaten alive last summer. The one below is an archaeological analogue, and that's from the Broxburn Hill Fort, which is just to the east, or it was just to the east of Edinburgh. It's been destroyed, I'm afraid. But there, archaeologists identified numerous, I mean, I can't remember, there's several hundred items were excavated of carbon steel, which has been heat treated and quenched. So far, nothing else has been done in either of these sites. But just to show with 2 quick examples, 2 very recent examples, that steel analogues can be found. And the question might be, should we actually start looking at them in the future, perhaps? And next one, please. So copper containers, archaeological analogues. Probably the best known, best studied is the Cronin cannon. It's a Swedish warship which sank in 1676. And when they actually recovered the cannon back in the mid-80s, they found that in general, even those which are sitting here, you see with the skull in the top picture, have only suffered minor corrosion despite the oxidizing conditions in the water. At slight depths in the sediment and clay, obviously it went anoxic. But it has been used, especially by SKB, as one of their arguments for the suitability of copper as a canister material. The recent POSIVA study I've got at the bottom there, 2023, there's a lot more examples of copper archaeological analogues, which if you're interested, you can have a look at. The Cronin cannon is actually on show in a museum in Stockholm now. And the next one, please, Sam. Natural analogues, again, going back to Tony Miladowski from BGS. Tony worked on this particular one, the Littleham Mudstone Formation in Littleham Cove in South Devon. And here we have sheets of copper, native copper metal, contained in a clay, which again is not a bentonite, but it does have high levels of montmorillonite. Interestingly, if you compare this with the several hundred-year-old Cronin cannon, the copper here appears to have been stable and has resisted corrosion for about 170 million years. As I say, they're somewhat longer than is required in a GDF safety case. Interestingly too, the clay environment, it's actually quite aggressive groundwater, much higher permeability. So again, it provides that warm tummy feeling, if you want. Makes you think, well, that's pretty good. If this thin copper plates can survive, then a thicker copper canister should do even better. Next one, please, Sam. This is a new one from MICA, the Michigan International Copper Analog Project, and thanks to Ismo Aaltonen from GTK in Finland for these figures, because his paper on it is just coming out. The first report is not yet finished, but basically they're looking at massive coppers in the Michigan copper field. And at the moment they're focusing on just general understanding of the site, understanding from baseline, so the bedrock copper, looking at cumulative corrosion and trying to assess which different periods of corrosion, when did this happen, when did that happen. Assessment of clay and copper. Majid mentioned earlier that the interfaces are important, and this is they're hoping to assess how much transport, for example, of copper into the clay has occurred, and has that affected the clay properties in any way. And also, especially for organizations such as Posiva, there's copper and copper sulfide systems. So they've got some nice material there where they've got copper sulfide and native copper coexisting, and trying to understand why. So NWS is involved in this as well, along with NAGRA, NWMO, SKB, and BGE from Germany. So it's brand new. I had a good chat with Ismo about it. Looks nice. They have some wonderful material, and it looks as if it will run for a few years. So keep your eyes on that one. Next one, please, Sam. Bentonite. Matt's mentioned bentonite as being rather important. So I put a little bit of weight on here, in part for that reason, but also in part because there's a huge amount of data on it, in fact. In general, we try to focus our analog studies on FEPs from the safety case to make sure they're meaningful. And if you look at this recent NWS, well, there's 2 NWS reports on analogs just coming out. If you'll get them, then there's a clear link to it. Here, however, I've used this table from JAE in 2005. This is more a requirements table they had at the time. They're looking at items, the buffer function that they required, and the buffer performance. It's just to, as you'll see in the next slide, please, Sam. There are just so many studies. There's so much information out there on bentonite. I just wanted to give you some examples. Again, all these references are at the back, the end of the presentation, and you can have a look at them there. But so looking at the functions as identified by JEA, restriction of groundwater movement, there's the IBL, the International Bentonite Longevity Project. Mechanical stability, there's LPB, that's long-term performance of bentonite. Barrier interaction, that's CNAP, BHS, that's borehole sealing with Nick Jeffries. There's the brand new KINA 1 project, which is just about to report, should be out by the end of this year. And that's looking at iron bentonite interaction from the Karuna mine. And there's a KINA 2 follow-up probably coming. Restrictions, radionuclide leaching and sorption of radionuclides haven't been touched, so I've just left them in black. Other things, self-sealing by Doro Yoshida, stress buffering, stability of disposal tunnels, thermal conductivity. I think Matt's mentioned thermal conductivity. That's one area. I've left it in blue. There's numerous studies, but I would say they're all irrelevant. They weren't done carefully enough, quite frankly. And there is a critical paper on them from 2015 that's worth having a look at. So as Matt was saying, you know, it is an area of interest, but I just honestly don't think any of the stuff that's been done on it is of relevance or has helped. It could be done quite easily. It just hasn't been yet. Permeability changes, IBL, restricting colloid migration, IBL. I've put that in italics because it's it's not easy. And I'll show you some images of the mine in a moment. It's a difficult site to do anything in, never mind that. Microbial impact, there's new work from Rachel Beaver from Canada, and there's something come out in the Keener report that it actually won't come out, the microbiology work, until next year, but it's there. And borehole tunnel sealing from the borehole sealing project, that's an NWS project. There's various reports on that. And then there's a NWMO of Canada work from 2015. In red though, and please be aware, there's a lot of rubbish which also claims to be bentonite analog studies. And I say there's the critical review from 2015, and there's some more work in the recent POSIVA report, which actually points out the problems. So please be aware. Just because it says it's an analog doesn't mean it's useful or relevant. Next one, please, Sam. So just a quick look at, because I mentioned IBL so often in the previous slide, this is the IBL site. The yellow part up in northern Japan there, it's in the Japanese Alps, the Sukinuro mine. The snowy pictures from 2016, but I was back there in January and there was about 4 meters of snow, so it meant surface field work was out of the question. The picture on the far right shows you it's not the best place to be working. I have been in safer mines in my life, but it is a unique, to date, a unique site to study bentonite because it's underground. Every other bentonite study has taken samples from a quarry or an open pit, as the Americans like to call open pit mine. The difference here, of course, is this is up to 300 meters deep. So we have full lithostatic pressure with conditions which are directly GDF relevant. If somewhat, I mean, you'll not see a GDF look like that picture on the right, though, believe me. Next one, please, Sam. So with IBL, we have very much focused on safety case features of interest. As it shows on the far right column, we specifically tied what we're trying to do to specific FEPs. As usual, in a project like this, it's funding organisations, NWMO of Canada, NUMO of Japan, and NWS of the UK. So everybody's got a slightly different direction they're pulling in, but in general, you know, focusing on the FEPs means, one, all three organisations get something useful out of it, and it means that the data we produce are of direct relevance to the safety case. Obviously, we need to produce some background information so we understand, for example, the full age of the site, we understand the water chemistry. But apart from that, we are very much focused on the safety case by focusing on the FEPs. That's not always the case, unfortunately. I won't go through this in detail, just to let you see that. Next one, please, Sam. Concrete. One of my favourite materials. I was a green young geologist. My boss at NAGA said, "You're going to look at concrete." And I thought, "Oh, no, please." Anyway, I've now got into it. It's actually very interesting stuff. And here I'm going to touch on two. We'll look at OPC, ordinary Portland cement derived concretes, archaeological and natural. And we'll also look at low alkali cement concretes, again, archaeological and natural examples. Next one, please, Sam. So OPC analogues, archaeological, we have things such as the picture on the right, the old mill from Swansea, built in 1898 and demolished in 1984. And the same guys, Mallinson and Davies, also looked at the first reinforced concrete marine structures built in 1899. They're interesting. I mean, they're not that old, obviously, but it is OPC, which is difficult otherwise. The CHS compounds and concrete from these two structures showed little or no degradation. We have to go back to stuff like this old work from Mallinson and Davies because nowadays we're just not allowed to do it. you ask permission to go and drill a hole in a nice, beautiful old archaeological example like that, and you'll get short shrift, unfortunately. So there is a limit to what we can do with archaeological analogues nowadays, especially when it comes to destructive analysis. For natural systems, one of the best we have and what's best studied is the Macron site in Jordan. The shot on the left, I'm standing on the top of the hill in Jordan, and that ridge you see in the distance is actually Syria. So it's right on the Jordanian-Syrian border. And this 2 million year old natural concrete, as you can see in the middle photograph, it repeatedly seals itself. There's some local tectonics going on in that valley, and the concrete fractures. And as far as we can see, it's difficult dating some of these. It's hard. There's a hammer on the right-hand side, the bottom right. It's not a very clear one, sorry. So it gives you the scale. These very fine fractures, they do seal, and they seal within decades to centuries. So we have a system that's 2 million years old, and it's completely and utterly sealed, apart from the odd tectonic reactivation, which then seals itself again quickly. Next one, please. Other OPC analogues. The one on the left, that's Scott Hill in Northern Ireland, again from Tony Miladowski from BGS. This is nice because it's 58 million year old concrete. And a bit like the stuff that we looked at in Jordan, when it interacts with groundwaters, it tends to seal itself naturally. And it was completely sealed for up until about the last ice age, probably, when erosion exposed it. But the areas that have been exposed and accessed by groundwater have sealed themselves really rather quickly. And for other areas, steel corrosion in concrete, for example, natural examples we haven't found yet, but there are information from some concrete chips. It's generally rather qualitative because the work wasn't safety case focused, but it's interesting. It shows that there's very little degradation, amazingly. Another FEP associated area is freezing and thawing. Most organizations think it's unlikely to reach the repository depths, but we can't really address it from analogues. There's none known at the moment. So to date, for organizations such as SKB and Posiva, they've used short-term experience and concrete durability from industrial use, which is completely understandable. The next one, please. Low alkali cement concretes. I've mentioned low alkali cements because mainly there's interest in them because the potential impact they have on bentonite. So bentonite's unstable in OPC pore waters, which start at 13.3. Low alkali, also known as low heat, low pH, or high strength cements, their pore water kicks off around 9 to 11. And in general, bentonite's pretty stable at that pH. There's not a lot of information on durability. And the oldest known concretes, man-made concretes, are only go back to 5000 BC from Serbia. But most work has been conducted on Roman concretes, which are from 3rd century BC, or perhaps the Romans stole them, as Middleton claims from his 1888 paper. Next one, please, Sam. And most of the data we have at the moment is from this Roman Cons group, the Roman Maritime Concrete Study, where the guys have been sampling lots of material all around the Mediterranean, mainly. And in general, it shows there's, at least for those few thousand years, high durability. And next one, please, Sam. How the Italians probably came about making cement is probably because it exists naturally there. And this is, if you go down to the Bay of Naples, there is some material there. It's not been studied much in detail because at the moment there's not that much an interest in low alkali cement usage, low alkali concrete usage, but there is information available, and I've actually looked at these sites myself. And the last one, Sam, if I may, just to round up. So the earliest mention of natural system materials or usage in GDF design goes back to 1955, when the US Atomic Energy Commission pointed out that working with natural materials such as bentonite, copper, and iron was a sensible path to pursue, as we have so much experience with them and have used them for a very long time. And that's actually quite true. It's a kind of no-brainer. To that list, I would add concrete and uranium ore, but I'm still personally dubious about glass. You know, and as the US Atomic Energy Commission pointed out back in 1955, you know, all these materials that they mention and actually look at are long-lived, and they are stable in a deep geological environment of a GDF. So, as I said there, as such, using analog data and the safety case is a no-brainer. But much other material is of questionable value, and most recent studies benefit from a focus on the safety case, and that's really the way we have to go. The next 4 slides are simply references for you to look if you so desire. But Sam, could you just pop to the very last slide, please? Just to say thank you for attention, and seriously, if you do have any questions, drop me a line at my email address. If I don't get back to you straight away, my apologies, but I will, I promise, get back to you and reply. Thank you.
Thank you very much, Russell. That was a very interesting presentation. I learned a lot. Thanks for that. I think we have time for a few questions, and suggest if you could write your questions in the chat box, or if you like to ask it directly, that's absolutely fine.
I guess I can maybe kick us off with one then.
Yes, please.
Thanks so much, Russell. That was really nice. Yeah, just to introduce myself, I'm Tony Yorkshire. I'm also a research manager at NWS as well. So I was interested in the Macarin natural sort of cement systems. Do you sort of know what the mineralogy of those sort of seals are? Are they sort of calcium silicate based or sulfate carbonate?
They tend to be a bit of a mixture. It depends. They're effectively mainly CSHs. Yeah, they are basically precipitating downstream. In some cases, if you have a younger groundwater that's coming in with enough bicarbonate still dissolved in it, and obviously you can get secondary carbonates as well, but that tends to be more surface. But yeah, it's effectively CSH phases and sometimes CASH phases, which when you think on it's not surprising really. The volume's that much greater anyway. And the big question there is that probably flow system there is a little bit quicker than we would expect in a GDF. And so perhaps some of these timescales that we talked about are conservative, because if you're in a more diffusive system, I suspect the fracture would seal even quicker.
Yeah, okay, great. Thank you very much.
Thank you very much. We have a question from Fiona, please. Thanks.
Your answer there, Russell, segues so perfectly into my comment come question. So this is we're looking at maybe Fiona Neal. I'm a ESC technical manager at the Low Level Waste Repository, and I've been working quite intensively the last 3 or 4 years on the near surface disposal silos. And these silos have 2 concrete walls with a bentonite barrier, so to basically create a hydraulic barrier around the near field and prevent advective flow. So one of the things that we've been looking at is these concrete walls, if you like, the shaft liner, and then within that the silo liner. But the shaft liner is quite interesting because it's a segmental prefabricated concrete segments and placed as the excavation goes on. And we were concerned that these segments would basically be a weak spot because there's a gap there. There's a little rubber gasket that maybe lasts 100 years at best. So we thought this is a real point of weakness. We're going to get quite a lot of alteration of the bentonite. But actually, I think this is one place where we've almost like done the opposite. We've seemed to have created an engineered system that is analogous to Macarin. So we've actually got sealing of the joints on a time scale, according to the modelling, that's shorter than the lifetime of the gasket. So essentially, the groundwater in the aquifer is quite rich in carbonate, dissolved bicarbonate. So it precipitates quite nicely. And so I think, if this project goes further than the current sort of feasibility project we've done, I think we'll be looking at natural analogues to support that understanding, because it makes quite a lot of difference to the performance of the hydraulic barrier over the long term, not the first few thousand years, but the sort of 50,000 year time scale. So we'll be going back to Macquarie, at least information.
Yeah, it's a nice site. If you ignore the poison snakes, the landmines, etc., it's a very nice site. No, it's interesting though, Fiona, because SKB, I was working on the SFL and SFR repository assessment with them, and their models were assuming complete dissolution of the concrete in 10,000 years, and I said, I'm sorry, that's complete nonsense. And we used the Macquarie system and in fact the Scott Hill system just to explain to the modelers, look, things do seal and they last very, very long time. And it didn't change their approach drastically, but they really scaled back the timescales, and they accepted that as direct evidence that, okay, maybe we are a bit fast. I also think Professor David Reed, who's just retired from Sussex, sorry, Dave, sorry. He said years ago, if these models were right, then there'd be no cities in the world because they'd all have dissolved already. And Dave's completely right. It's a nonsense. So I'm glad to hear that you're heading that way too.
Yeah, thank you. Interesting talk as well. It's nice to refresh my memory.
Thank you very much. Is there any other question? Okay. Yes, Matt, please.
Yeah, it's a quick one. So in UK GDF siting process at the moment, it's quite dynamic with new sites coming on, or with having their own emerging uncertainties. So I was wondering, how would you identify new natural analogues to kind of think about those uncertainties? So, for example, we could potentially be in a briny environment, which can impact the performance of these barriers. So, kind of, how would you kind of identify these kind of new analogues?
I mean, the easiest thing is it's just an awareness of the environments that are out there. I mean, again, if you ask around as well, I mean, Macquarie just happened to be, discussions at a conference over a glass of water or something, I believe. So there are probably examples to cover most aspects. I specifically mentioned the Magnox fuel because that's one we can't do. But there are other ones out there, and it's a case of, if it comes up in the safety case or in the site characterization that there is a requirement, then you can say, well, sure, I know of something, I know of a guy who knows of something. So it's, I'm not saying there's something for everything, but if you look hard enough, you'll find it. Like, I never really, when I was told I was going to be working in concrete, I thought, but it's turned out to be fascinating. I mean, I hate to say that, but concrete is fascinating stuff. And, it's taken me to Jordan and Syria and other places to study it. So, yeah.
Thank you.
Thank you. One question from Gary.
Yeah, it's not so much a question. Thanks for the great presentation, Russ. I really enjoyed that. And I also find concrete fascinating. What I learned today, though, is that the Weaver building in Swansea, I'm from Swansea, they took us there to see bits of it blown up with the school when I was 6, I think. And I didn't know that was the first reinforced marine structure. So that's a great bit of local knowledge that you've passed on. So thanks a million, Russell.
Yeah, if you have a look at that paper, it's in the reference list. It's quite interesting.
I'm on that now. Thanks very much.
Pleasure.
I think you muted, Majid.
It looks like there is no more question. I would like to ask one quick question, which is linked to the other two speakers after the break. Other evidences, natural evidences that indicate bentonite would tolerate and perform at an acceptable level at elevated temperature.
Yeah, I mean, I was a bit scathing when I said that there are no thermal bentonite analogues. There are several sites which exist, but they weren't studied properly, is how I could put it. The guys were interested in very high temperatures. They were looking at 1200, which is not relevant, or they were just focused on the mineralogy, so didn't examine the wider aspects to put everything in context. So yeah, there are several sites, yeah, and if you look at the it's a POSIVA, it's a reference to the 2023 report on the complementary considerations. There is actually a discussion in there on it, because POSIVA, like NWS and other organisations, are also thinking about how can we reduce the footprint. So yeah, I would say definitely, yes.
Thank you very much. Appreciate it. There is also a link to the RSO website and registration for the newsletter if you are not registered.
Yeah, just say thanks to Russell for giving the presentation. It's really useful. Thank you.
Pleasure.
I think it's you started, isn't it, Rebecca? So just to introduce Rebecca, a student at Strathclyde looking at cement performance at high temperature. So I'll leave it with you.
Cool. Shall I share the slides?
Yeah, go for it.
Okay. Can everybody see this?
Yep.
Yeah, that's great.
Okay, cool. So as was just said, I am Rebecca. I'm a student at the University of Strathclyde, and my PhD project is funded by NWS, and it's called The Effect of High Temperatures on NRVB Cement. So these are sort of the overall current aims of my project. So to look at what minerals are actually forming in the NRVB at these high temperatures, and then to look at how they actually are affecting the properties. So it's to look at how the different mineralogies are impacting the water transport properties like porosity, permeability, and chemistry. And then also how do these new minerals actually affect and control the radionuclide transport? So what is NRVB? So NRVB is one of the proposed backfills, and it's a reference backfill. It's low strength, high pH, and low viscosity. So it's made of 4 different components. It's OPC cement. So this is what provides the overall strength through minerals like A-lite and B-lite that's set. It's made of calcite, which is a fill material, calcium hydroxide, which is also known as portlandite, and this is what provides the high pH over time. And also, it has quite a high water amount, and this is what is giving it a low viscosity and also is reducing the strength. NRVB has a very high calcium oxide to silica dioxide ratio, so it's about 7.27. There's limited data of the mineralogy that forms at these high ratios, and particularly at these high ratios at high temperatures. And also, if ultimately a higher strength cement is wanted, one of the ways it's done in industry to increase the strength of cements is to add more silica dioxide and reducing the ratio. And so looking at this lower ratio cement at higher temperatures is also useful to do. So, oops, sorry, I'm trying to, there we go, okay. So this is the methodology that I've been following to look at the first aim, which is what I'm going to talk about today. So the 4 components are mixed for 15 minutes until you get a homogeneous mixture. We've then developed with the technicians here these various these molds. So these are important because the cements, you get like little 5mm cores out at the end. So you don't need to use any machinery that could increase the heat of the cement, or also if you need to use coolant, this can contaminate the sample and also make other reactions take place. So you're basically getting out exactly at that time point the products that you're forming. They're then put into a vacuum chamber for 15 minutes. This is to remove any artificial porosity that you might get. So the only thing, you're not getting any air bubbles inside. They're then cured for 5 days at whatever temperature you want to look at that point. They're then carefully removed. These cores are then doped in isopentane that's cooled using liquid nitrogen. They're then freeze dried for 24 hours and they're weighed before and after to make sure that it's losing its pore water. So this is to arrest the hydration so that the minerals that you're getting out don't continue to evolve and develop. So it is representative of that time point. They're then ground to have a particle size of less than 10 micrometers before being measured using X-ray diffraction. So they're ground to be very small so that you get a proportional measure with the X-ray beam. Cool. So these were initially cured at room temperature 80 degrees and 200 degrees, and silica dioxide was added so that we had the ratio of NRVB, which is 7.27, then more silica was added to reduce it to 7, then 6, then 5, and then 4. This is because there's already quite a lot of research up to a mineralogy of up to a calcium silica ratio of 3. So these are the XRD patterns that I got when the NRVB cement was cured at 200 degrees. So as you can see from this, the only minerals that you can really identify are the calcium carbonate, which was put in at the beginning, and also the calcium hydroxide. So as you can see from this zoomed in peak, as you add more silica dioxide, so you're reducing the ratio from 7 to 4, the amount of portlandite decreases. This shows that it is participating in a reaction. However, the amount of calcite remains stable, so it remained constant no matter how much silica you put in or the curing temperature. So this shows that the calcite is dominating the XRD patterns and making it very difficult to identify any smaller phases. If I just go back, you can't really see any other peaks, and you definitely can't identify them accurately. But also the calcite doesn't seem to be reacting. So I thought the solution to this was to remove the calcite, but then adjust the solid to water ratio so it's consistent, so it's still representative. However, because the portlandite is reacting, it needs to stay. So here are some patterns that don't have any calcite. You can kind of see that now there are a few more peaks. So I've just labeled the graphite peak as an example, which you can more clearly see in the NRVB N7 sample. So other minerals are now present in a proportionately larger quantity, and they can now be identified. So here are all of the results with the mixes made without calcite. So these were made again from a calcium silica ratio of 4 and then all the way up to NRVB, which is 7.27. These were also cured at 25 degrees, 80, 150, 200, and 250. These temperatures were chosen based on existing mineralogical diagrams that show that at these temperature steps, you do get quite different mineralogies forming. And this was just to see if that still applies at these higher amounts of calcium oxide. So I'm just going to talk through a couple of the minerals here that I think are interesting. So I've just highlighted here these. So the one I've highlighted is the portlandite. So this is the calcium hydroxide that is responsible for the high pH. So here's a heat map showing the amount of portlandite, where black is 100% and white is there 0% present. As you can see from this, at a calcium silica ratio of 4, so the highest amount of silica dioxide addition at 250, there is no portlandite left. So that means you don't get that long-term pH buffering. At the NRVB samples, you still have some. But yeah, so it's entirely consumed by the reaction at this higher temperature. And as you increase the temperature along all of the ratios, you are getting less and less present. So, however, you are also getting new minerals formed. So I'll just go back to here. So these 4 minerals here that I've circled, these are all strength reducing minerals, but it is worth saying that some studies have found that at higher temperature curing, there is a microstructural coarsening within the cement that is also reducing the strength. So these 4 minerals are alpha C2SH, gamma C2SH, graphite, and Reinhardt bronzite. So here are some more heat maps. So on the left, we have the heat map for the alpha C2SH, and then on the right, we have graphite. So these have similar properties. So alpha C2SH forms from a recrystallization of calcium silicate hydrate. It has a smaller unit cell. So the unit cell is the smallest repeating unit. So it's like the smallest little chunk of carbon and calcium that you can get when you break it down. This means that because it goes from larger to smaller, there's a shrinkage. This leads to a porosity increase, and it's called strength retrogression, because I don't know if you can imagine like squeezing a sponge, you're going to get gaps and it's going to crush it. In the oil and gas industry, this is prevented by adding more quartz powder or silica dioxide until you're actually reducing the ratio to 1 or below. Graphite has similar properties, and it causes the pore structure of the cement to degrade when it's forming, and this leads to a strength reduction. So the alpha phase is forming at 150 degrees, and then at some of the ratios at 200 degrees, so it's only a problem there, whereas the graphite is forming at 200 and 250 degrees. Then the other two minerals that are strength weakeners are Reinhard bronzite on the left and this gamma phase on the right. So with Reinhard bronzite, this is a weakener because its crystals form like they bond poorly to each other and they're quite long, so this leaves gaps. This means the structure is loosened and it leads to an overall strength reduction. This gamma C2S phase, it actually forms from B-light. So the B-light, which is the long-term setting mineral, becomes instead this weaker one. So it's larger than B-light. So again, if you can imagine something going like growing, then this creates dusting. And it is a weak phase with low hydrolicity, but some studies have found that it has a high affinity to carbon dioxide. So this means it could be useful for capturing carbon-14 potentially. In the lab, I've also observed that above 150 degrees, the cements are incredibly weak to touch. So at 200 degrees, I have to be careful picking them up with tweezers because sometimes they just go poof and you just get a dust. And at 250 degrees, they're actually too weak to handle. So to get other measurements where I want to look at the porosity, I have to cure them in special tiny molds that can be fitted into the machines. I keep trying to use the keypad, but it doesn't work. I have to click. So then the last phase that I'm going to talk about is this one that's kind of hot pink down in the corner. And this is only present at calcium silicate 4. So this is about 19% of the cement is replaced with silica and at 250 degrees. So xenolite is needle-like strengthening and dense, and it gives extra strength because of its high density. It's thought to form from portlandite reacting with silicon dioxide, and also a polymerization reaction when you have the CSH dissolved and the silica SiO2 dissolved, and it's basically like the end sites polymerizing. So I think I have a couple of minutes. I'm just going to talk about this a little bit. So this is the second aim. So this is what's happening to the mineralogy and water transport properties. So the difference in preparation for this is the same cores are coming out the oven, so it's the same mixture, so they should be comparable. But instead of being freeze-dried and ground, which destroys the microstructure, they're soaked in alcohol for 3 weeks. So the alcohol replaces the water inside the pores and still arrests the hydration. Then some of these have been scanned with the XCT machine and others have been embedded in resin. So this is macroporosity from the XCT scanning. I'm just going to mention, I've also looked at the microporosity, which is about 40 to 50%, which is what's seen in papers and industry. But the macroporosity is from scanning, so it's quite impacted by the resolution you can get. So if you're not getting a particularly great resolution where you can look at tiny micrometer measurements, you're just going to see the larger pores. So I found that with the NRVB samples, as the curing temperature increases, you get more porosity, which I think makes sense because when you boil a kettle, you get more bubbles. But when you add silica to it, it actually seems to decrease to 150 and then begin to slowly increase again. I'm just going to show some pictures. So these are the XCT scans from 150 and 200 degrees. So which I think is quite interesting because as you can see, there's a change in the pore shape. So at 150 degrees, they're kind of more spherical, which is what you imagine when you think of a pore. Well, I do anyway. But then when you increase the temperature to 200 degrees, the NRVB samples are kind of more horseshoe shaped, whereas the higher silica addition samples are kind of a donut shape. I think this is interesting because you are also changing the mineralogy. So what's growing inside these pores? So I know the mineralogy and I know the pores are changing shape, but I don't know what is growing within these. So we actually have plans in the new year to go down to the diamond beam line and use their diode facility. So this has the capacity to XCT scan them, so you're getting these images, but then you can also click and it gives you an XRD pattern, so you also see what's where. And then here are some pictures from the EMPA measurements. So this is being used to confirm the mineralogy and the porosity. So the pores can be confirmed because you get this high carbon content. So they're embedded in resin, which is high carbon. So you basically look for that. Then I look at the elemental map of calcium, and there's no calcium present, so that pretty much confirms it's a pore. Then lay the silicon map over the top to see if it is an actual calcium silicate mineral or just Portlandite forming. And here it is, if you can see, it kind of goes a little bit purpley. So this means there is a calcium silicate mineral forming surrounding the pores. So this means that it will be interesting to actually go down there and see what exact mineral is there. So the formation of high temperature minerals is consuming the Portlandite and reducing the strength. But then the next question is, how are these actually affecting the radionuclide transport? So I'm going to synthesize pure single phase minerals and then actually see what happens when I mix them with radionuclides. Because if you're losing the Portlandite and you're losing a bit of that pH stability, but you instead have like this gamma C2S phase that's absolutely brilliant at sucking up radioactive carbon, you know, could you adapt the formula so that you get both? But cool, that is the end. So thank you for listening. Are there any questions?
Thank you very much, Rebecca. Very interesting presentation. Is there any question for Rebecca?
I can
Yes,
ask a question if that's right. Thanks, Rebecca. That was really nice. You've got some really nice data. I just wondered, you mentioned about the different minerals that are either sort of strength inducing or strength reducing. Have you done any compressive strength tests, or are you planning to do any to look at the kind of the change?
Yes, I'm planning to do them. So before I go down to diamond, I need to basically remake all of them out of far smaller. They need to be smaller than 3 mm diameter. So I'm going to also cast some for the strength testing at that point as well.
Yeah, it'd be really good to see the pattern over the different ratios and the temperature, just to see how those sort of minerals are trading off and the change in the strength. But yeah, really nice. Thank you.
Thank you very much. Next question, is there any? Okay, could I ask a quick question? Following what Tony asked, if you would do a strength test, would you do that at elevated temperature?
No, I would think to do it like to make the mineral and then test it after it comes out. I think we have capacity to potentially do that, but I would have to ask around and see if I could do it before I did it.
So basically the scope is now to look at the curing temperature and its impact on the kind of microscopic properties. And then hopefully in future there will be some mechanical tests.
Yeah.
Okay, excellent. Thank you.
Thanks.
Thanks again, Rebecca. Pass on to Matt to introduce.
Yep. So we now have Stamatina talking about bentonite performance at high temperatures. So over to you, Stamatina.
Hello, thank you very much for inviting me to present my PhD research topic. I will share my screen. Okay. Great. Okay, so my name is Stamatina Alexandropoulou. I'm a 30-year PhD student in Geotechnics group at Imperial College London. My PhD research topic is about modeling the behavior of compacted bentonite at high temperatures up to 200 degrees, and this is a PhD which is founded by the EPCRC Center for Doctoral Training in Nuclear Energy Futures and Nuclear Waste Services. My supervisors from Imperial College London are Professor Lydia Strakovic and Professor David Potts, and from Nuclear Waste Services, Dr. Matthew Kirby, Dr. Simon Norris. In the next slide, I have included an outline of the presentation. First, I will start by introducing you to the background to PhD research project. Then I will talk about the methodology and in particular in terms of constitutive and numerical modeling that have been adopted in this particular PhD research. After, I will present you a numerical validation example of vapor flow in one-dimensional thermohydromechanical couple soil column problem and its results. And then I will conclude by showing you the next research steps that have been planned up to the completion of my PhD project. To start with the background to PhD research project, the challenge that I'm working with is the long-term disposal of high-level nuclear waste, where the proposed widely accepted solution is the deep barrier in a geological disposal facility. My PhD research topic is at the end of the nuclear fuel cycle. So not really about the production of nuclear energy, but what to do with the waste which is generated from the operation of a nuclear reactor system. So as we can see here, we have an engineered barrier system. So the approach is the use of these systems, which is a multi-barrier system approach. Therefore, the waste will be placed inside the canisters, which are made of stainless steel or copper, and their high temperatures will be developed. And if at any point in time this canister will corrode, the radionuclides will escape into the natural environment. Therefore, it is important to prevent this from happening, and therefore we are using buffer materials, which are mostly bentonite-based materials. And we have also natural barriers, which is the geosphere and the host rock formation. Bentonite material, the bentonite is what we will investigate. I'm investigating in my PhD research project, and particularly I'm looking its behavior under high temperature conditions. So bentonite during its installation phase is unsaturated and also is compacted, that can be installed either as bentonite blocks or granule pellets. So if we look here at this image, for example, on the left-hand side, we can see the bentonite blocks, and then here will be placed the nuclear waste canister, while on the right-hand side, we have the waste, which is placed inside the nuclear waste canister, and this is placed on the top of bentonite blocks, and the filling is made using bentonite granule pellets. The challenge here is that the compaction creates a double porosity structure, which is responsible for developing ideal properties. And because it is a clay, if we are using a microscope, this is the formation that we can see. So as we can see here, we have as a clay aggregates, and between them we have some voids, which consist of microstructure or microporosity. Whereas each aggregate has clay pellets, and there is also porosity in each aggregate itself, which is called microstructure or microporosity. Sorry. Okay. Okay. So further to this, within the environment of the deep geological repository system, complex thermohydromechanical interaction in bentonite barrier will take place. So if we look again in this image, in the middle we have the nuclear waste canister, which emits heat towards the bentonite buffer, and then the interface between the host rock formation and the bentonite buffer material is subjected to wetting from the water that comes in from the host rock formation. Therefore, the objective is from the bentonite barrier material to possess some ideal properties. So first, to have high dry density to promote swelling country saturation, and particularly if we go back again and we see on this image on the left hand side, we can see that there are many voids, so the ceiling is not full in the interface between the bentonite blocks and the a host rock formation. So upon contact with water, the bentonite material will expand, and with this expansion actually, swelling pressures will be developed. Just to mention here that these swelling pressures should not be higher than the strengths of the host rock formation, otherwise they will crack the rock. Another important property of bentonite material is that it needs to have low permeability for solid irritation. And just to explain that is because actually of the double porosity structure that we saw right here. Upon in contact with the water, the clay aggregates will expand and will fill these voids that we can see here. So the microstructure will dominate over the macrostructure. And therefore, that means that the permeability will be reduced. And if at any point in time, because of the long-term corrosion of the nuclear waste canister, radionuclides will escape, this process will be really slow. So this is a very important property from the bentonite material. Now, if we look at the level of geological disposal facility, this thermohydromechanical bentonite evolution takes a lot of time, and also it has effects on the host rock formation due to temperature changes and pressure changes, which last up to thousands of years. The research community internationally, in order to understand this complex thermohydromechanical interactions within the bentonite barrier into the repository system, has developed laboratory scale experiments as well as in situ large scale experiments where heaters are used rather than actual waste. And that means that here the objective is that appropriate numerical models should be developed in order to be able to simulate accurately these experiments, which have a limited sort of time compared to the long life cycle of the geological disposal facility and the long half-lives of the radionuclides included in the waste. And of course, the objective is that these numerical models can perform predictive analysis, so to extrapolate what will happen in the future in the bentonite. Therefore, my PhD research aims is first to investigate the thermal constraint on bentonite buffer at high temperatures up to 200 degrees Celsius to identifying key thermohydromechanical processes and also to perform predictive analysis when very poor flow is included. After, to provide guidance on repository design and the maximum thermal output to ensure the safety of natural environment and to address the question if the current models that have been developed for experiments up to 100 degrees Celsius are suitable for higher temperature conditions up to 200 degrees. Because the last 2 decades, the experimental efforts have been focused in a maximum temperature limit of 100 degrees. Therefore, there is the recent tendency of going up to 200 degrees. That means to store more waste in one individual canister. Therefore, more energy will be generated and the temperatures will be higher. But the question here is how high until the safety of a geological disposal facility will be compromised. Having discussed about the background PhD research project, I will continue with the methodology that is followed for a numerical analysis in my PhD project. So we use the finite element software ICFEP, which has a fully DHM coupled formulation for saturated and unsaturated soils. And here I will not talk much about this equation, but I just want to show you that this is the DHM finite element formulation for unsaturated soil in the soils in the incremental matrix. Just only to highlight that the terms in various matrices depend on soil properties such as stiffness, strength, permeability, conductivity, which vary non-linearly with changes in displacement pour water pressures and temperatures. And also these here that I have with a red color are terms which associated with the formulation that accounts for the vapor transport in pores due to heating to high temperatures. Also, the double structure constitutive model is used, which has its conceptual basis on a Barcelona expansive model, and this is a model that has been previously used successfully for simulating the Webex large-scale experiment at temperatures up to 100 degrees. Next, I will present you one of the simulations that I have performed during my PhD project. So this is a numerical validation of the vapor flow in the developed nonlinear DHM finite element formulation. And as we can see, we have a cylinder. In the middle of the cylinder, this in brown color is the bentonite material, which has this height, this diameter, this initial solid suction and initial relative humidity, and across the cylinder there are sensors that measure relative humidity and temperature, and the experiment applies a temperature gradient on the bottom actually of the cylinder by heating, while the top of the cylinder remains stable at ambient temperature of 22 degrees Celsius. Also to mention that after 65 hours, this bentonite sap is weighted through water that flows from the top of the cylinder, and this has 1.2 megapascal pressure. And here in this slide, I have included the finite element model that we use to perform these simulations. So we can see the thermal boundary conditions and the hydraulic boundary conditions, and also the temperature and relative humidity measured at 3 elevation levels within the samples that are recorded here, right here. And then on the left-hand side, we can also see an equation that describes the diffusion vapor flow. The first term shows the vapor flow due to changes in suction, while the second one presents the vapor flow due to changes in temperature gradient. And in the following slides, I have included some of the simulation results against the experimental data. So here I have the temperature evolution at these three different elevation levels, points. So as we can see, the point, this one, which corresponds to the monitoring point, which is closest to the heating, has the highest temperature, which is established after almost 10 hours, 50 degrees of Celsius. And this, let's have a look on the furthest points, which establish the temperature of almost 20 to 25 after between 10 to 20 hours. And as we can see, our simulations predict quite well the experimental data. In the next slide, in a similar manner, I'm presenting the results of relative humidity in terms of time. The relative humidity is calculated through the suction, which is actually the negative pore pressure. It's just to mention here that this is initial increase that we notice is due to temperature and to vapor flow, because the vapor flow is migrating and then condensating, so increase the relative humidity here, but as the heating progresses, the bentonite samples dries out, so that's why after the relative humidity decreases. And just to mention that these results correspond to the point which is closer to the heater. In the middle point, we can see that our model predicts it a bit faster compared to what actually is recorded. And then the last monitoring point, which is furthest, away in on the top of the cylinder, in the wetting boundary. We can see that wetting is dominating, so it's close to full saturation. And just for demonstration purposes, here just to mention that I have set this term in the equation that I showed you previously, and this term here is related with the vapor flow. I have set it equal to 0. So as we can see, temperature evolves in the same manner. It is not affected by the lack of the vapor flow, while when we look at the results of relative humidity versus time, we can see that very much is affected this abscess of vapor flow of this term right here, because especially in the starting point, this 0.1, which is closest to the heater. So as we can see, it cannot predict this initial increase in relative humidity, and also it increases very fast, which is due to suction, which is something unrealistic. The rest points are doing better in terms of prediction, simulation results. So just to conclude here, that this shows the importance of the inclusion of vapor flow in the DHM formulation. Having discussed this, I will close this talk by presenting you the next research steps. So further validation tests in high temperature environment above 100 degrees of Celsius need to be done. So I have here some sets of in situ experiments that have been previously conducted. This is up to 150 degrees and this is up to 140 degrees. And these simulations are important because actually we would like to test where our numerical tools will break down and will not be any more efficient in predicting what is going to happen in the evolution of the bentonite material. After that, we will continue with the hot bed lab test, which is an experiment, laboratory scale experiment up to 200 degrees, and has been developed in support of the large scale hotbed experiment. Here we can see the hotbed experimental layout and instrumentation. And just to say that this is the main experiment of my PhD research project and the connection with the nuclear waste services. So this experiment is performed at a range of temperatures between 175 and 200 degrees. It includes 2 different types of bentonite. And these large-scale experiments are important in order to address some inconsistent results that have been previously recorded from experimental investigations. Just to give you an example, I have included some bentonite properties and how are affected due to high temperatures. These are results from laboratory tests. And for example, if we see at the swelling pressures, we can see that different studies predict different results, increase or reduction, or with green color, we can see that the swelling pressure actually remains stable with the temperature increase. The thermal conductivity again seems to does not very much affected. Only between the temperatures of 100 to 150 degrees Celsius there is a slight increase, and then the hydraulic conductivity increase with a temperature increase. So these are the things that we need to address upon until the completion of my PhD research through numerical modeling. And just to conclude, understanding and modeling of thermohydromechanical interactions in bentonite buffer is critical. Experience has already been gained for DHMC processes for low temperatures up to 100 degrees, but now we have to investigate what is happening up to 200 degrees. Satisfactory simulation results from the column test experiment that I just presented you. However, we saw the importance of vapor flow in the numerical formulation. The address that needs to be the question that needs to be addressed is if these numerical models that have been developed for temperatures up to 100 degrees are suitable for higher temperature conditions up to 200 degrees Celsius. And finally, further validation numerical tests of laboratory and field scale experiments at high temperatures are needed to address inconsistent results on bentonite properties that have been recorded in previous investigations. And here I have included a list of references in case you are interested in, and thank you very much for your attention.
Thank you very much for your presentation. That was very interesting. It's a very challenging work. Well done.
Thank you very much.
Is there any question? Okay, so I have a quick question. I know that we are a bit exceeded the time.
I'm sorry.
In your model, would you consider liquid flow in the vicinity of the heater or just vapor flow?
No, we include also the liquid flow in the simulations, for example, that I showed you previously. But yes, what I actually saw by the simulation was the importance of vapor flow, especially close to the heating, in order to reproduce the experimental results.
And what is the what is your conclusion about the importance of the liquid flow compared to vapor flow? Because the liquid content should be very, very low at the vicinity of heater, correct?
Yes.
But there is a still movement of water in the forms of liquid.
Yes, that's correct.
Is that so important or unimportant?
So I think the thermohydrochemical interactions that take place are quite complex. So what, for example, I saw with these simulations that I have performed so far is that the vapor flow needs to be added, particularly in the formulation, because has an effect in because due to high temperature creates evaporation, and then the condensation increase the relative humidity. But when you go away from the heater, actually, this the wetting is dominating. So I would say that when you look from the perspective of closer to the heater, the vapor flow, the importance of accounting for the vapor flow is important, but both has to be considered in the numerical formulation.
Thank you very much.
No worries.
So it looks like there is no further question. I think, Matt, would you like to conclude? And
yeah, just say thanks everyone for joining, and sorry, slightly delayed, and thanks very much for the great presentations today. So wish you all a good week. All right.
Thank you.
Yeah.
Thank you.
Thanks,
Bye.
everyone.
Bye.
See you in next webinar, hopefully, and perhaps in our workshop. All the best. Bye-bye.
See you.
Bye.
Bye.